got, what was I going to say? We got the holiday on Monday. Yes. So make sure you take advantage of that, because after that, man, there's nothing to it. I guess we get Veterans Day off, November 11th, and then that, but it comes boom, 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 boom. What else was I going to mention? Oh, for those, I noticed, I know I tend to, in this class, get a lot of pre-pharmacy folks, and especially for the folks who are transferring in or relatively new. Just wanted to mention the pre-pharmacy group, the FPSO, is at their initial meeting on Wednesday evening. Is that right? Somebody from the FPSO here? I don't know. Anyway, that's it's a great group. If you're interested in a career in pharmacy, I encourage you to get there. A couple years ago, we had a great group of students get into pharmacy school. I think from terms of like biochemistry majors, I'd say 80 or 90% of them got in. And I'd like to think it's something that we're doing in our curriculum here, but honestly, I think it was the power of that FPSO group in terms of getting people at pharmacy schools to come here and talk about the application process and visiting schools and understanding what you really need to get in and all that sort of stuff. So if you're into pharmacy, I'd encourage you to get involved with the FPSO. Same thing with pre-dental and all the other pre-health. The student organizations can be very helpful. Anything else going on? Oh, okay, we're going to start talking about chemistry of water. One of the things I put on the Mastering Chemistry thing, you'll see there's an assignment up there. I can't remember what the word is for it. But it's basically, it's a practice. It's one of these things that leads you through buffers and all sorts of stuff. There's no points associated with, but it's something that the publisher provides. It's basically a series of practice questions, more or less. It's like, and you click on it, and if you click once if you kind of know the answer, and you click twice if you really know the answer, and if you only click once, then they'll give you another problem like that to really test you to see it. It's just kind of practice kind of thing. So feel free to take advantage of that. There aren't any points involved with that, but at least it's a tool that was available from the publisher, so at least make sure that you guys were aware of that tool. But then the homework that there are points associated with is up there, and what's the date I have for the due date? But you should be keeping up on that for, all along. Yeah, the due date, I guess it is next Wednesday. Next Wednesday is the due date. So get that going. A lot of buffer problems. All right, speaking of getting going, I got to get going. All right, so we talked about, we finished up by talking about the hydrophobic effect, right? So now what we're going to do, we're talking about water. Here's this environment that aqueous systems put into, and we're going to talk, we sort of talked about sort of the nature of the hydrogen bonding and how that ends up influencing the physical properties, and talking about how that drives the hydrophobic effect. And now I want to get into a little bit more of the chemistry of water. Okay, so let's first talk about the fact that the ionization of water. That if you have two water molecules, that they can actually split, this is very much a reversible process, to form one of the hydrogens will come off one of the molecules and join another one, so you get this transient H3O plus, then plus, and OH minus. Now, the problem with, this is more likely the physical reality, is that a hydrogen gets transferred from one water molecule to another molecule, okay? But in fact, it doesn't stick around in that one molecule for very long. It actually kind of jumps all over from water molecule to water molecule. It's never really free independently. It's also always associated with the molecule, but it's kind of bouncing around. So to kind of more reflect that matter and get to simplify things, we can also talk about sort of depict the ionization of water as the water molecule splits into an H plus plus an OH minus. Even though that H plus is actually always associated with another water molecule. Now we can write an equilibrium constant for this reaction, in which we have the products of the reaction divided by the reactant, essentially water, like this, like such. Now, I've written this as concentration. The more formal way of doing it is actually with activity, and your book talks about this a little bit. I'm not going to get into all that detail. I'll leave that between you, Dr. Gurman, basically. We can take to PChem to get into that in a little bit more detail. The important thing I'm basically going to take out from this is that we can define a quantity known as the ion product of water, which is the concentration of H plus times the concentration of OH minus, and that equals 10 to the minus 14 molar squared. And it's a constant. So that if we have more H plus, we're going to have less OH minus. So if we have acidic solution, we're going to have a lot of H plus in there, and correspondingly we're going to have lower amounts of OH minus, and that's going to lead, it's always going to, the product of that is going to always equal 10 to the minus 14. So all this stuff should be hopefully moderately familiar to you. Now, in pure water, OH minus equals the concentration of H plus, so that OH minus is the concentration of OH minus, we go back over here, the ion product water, this is 10 to the minus 7 molar, this is 10 to the minus 7 molar in pure water. So that the concentration of H plus equals 10 to the minus 7 molar. And again, kind of remembering some general chemistry. So we go, that's a kind of a difficult, always dealing with those exponents is kind of difficult. So you have this P system. This P means take the negative log, base 10 log, so that we can talk about the P of H plus is the negative log of this, which equals 7. So pH equals 7. So that gives a little bit of a reminder of how we're getting there. Now, one of the things I want to do is, we talk about this ionized water, 10 to the minus 7 molars, kind of give you a little bit of understanding of actually how rare of an event that is. Okay, so that, say we took a whole bunch of water molecules, pure water, and lined them up in a line, and say we're going to change the scale. So now a water molecule is like a foot. Every 3 feet or so we have a water molecule. Okay, we would come across an ionized water molecule, one of these H3O plus water molecules, every 314,772 miles. Over 12 and a half times around the circumference of the Earth we'd have to walk before we actually came across an ionized water molecule. So, in spite of, we talk about acidity all the time, but we have to recognize that it's really a pretty rare event. But in spite of that scarcity, that rarity, it actually is quite important. And the difference between a solution at pH 7, in which you're coming across an ionized water molecule every 12 and a half times going around the Earth, and pH 4, because we remember it's a log scale, at pH 4, it's 1,000-fold less than that. So at pH 4, more acidic, you're coming in across a water molecule every about 314 miles. Okay, so between here and LA, at pH 4, you'll come across one. And if you come, if it's at pH 10, a relatively basic, you have to go around the Earth 12,000 times before you actually come across one of the H plus molecules. So again, it's a rare event, but there's a big difference in chemistry between what goes on at pH 4 and pH 10. So in spite of that rarity, the difference in the frequency of that actually makes a big difference. All right. Now, so that's basic properties of the ionization of water. Now what I want to get into is start talking about molecules, buffers. And, buffers are very important in biological systems. They're also very important in operationally when you're doing laboratory biochemistry. So we'll talk a little bit about that. All right, so buffers. Buffering is a property of weak acids and bases. So let's first talk about, what do we mean by a strong and a weak acid and base? So if we talk about a strong acid, that's something like HCl. And HCl, when it dissociates, it makes H plus Cl minus. In an aqueous system, that's a pretty highly spontaneous reaction. It goes all the way, basically. And so pretty much as much HCl you put into a solution, that's how much H plus that you're going to get. It's a strong acid. It totally dissociates. If we're talking about a strong base, NaOH is a strong base. Put NaOH in solution, it's going to dissociate Na to OH minus. Okay, but if we compare that to a weak acid, an example here I use is acetic acid. It can also dissociate. But this is actually quite a reversible process. Doesn't necessarily all dissociate. A little bit of terminology, because before I go on from here, we talk about this is the acid, and this is the conjugate base. Often this is abbreviated HA, and this is abbreviated A minus. So now what we can do is we can make a solve for an equilibrium constant for this reaction. Again, where we put the products over the reactant. So we have H plus A minus over HA. This is an acid dissociation constant. This gets basically a special name for its equilibrium constant, and that's Ka. Now what I'm going to go through here is I'm going to drive an equation for the relationship between the ratio of A to HA, the ratio of the conjugate base, that is, how much of this is really dissociated relative to the concentration of H plus, relative to the pH. Okay? This equation was originally worked out by a guy named Henderson, and then a guy named Hasselbalch actually did it in logarithmic form. So the equation known as the Henderson-Hasselbalch equation. I was kind of curious. I had been teaching this for a while. I thought, who is Henderson? So Henderson, turns out he was a professor at Harvard in biochemistry and physiology, and around between the 19th and early 20th century. So there's like late 1900s and early, late 1800s and early 1900s time. He was also interested in sociology, and he also was history. And he wrote a book about sort of how important environment is to living systems. He was very interested in aqueous systems, control of pH, and we'll talk about the carbonic buffer system, which regulates pH in blood. He was very interested in that and did a lot of studies on that. He actually wrote a book, I can't remember the title of it off the top of my head, The Environment and the Fitness of the Environment, that's what it's called. The Fitness of the Environment, that argues basically, why is the environment so good for biological systems. It was published in the early 1900s, but still kind of an interesting read, and particularly the chapter on water. So I went ahead and posted it on SACCT, so if you're interested, it's a link to it. It's one of these free Google books. And so you can link and you can check it out. I'd have a look at the chapter on water. It's pretty informative. Okay. So anyway, what Henderson did, and then subsequently sort of modified by Hasselbalch, is say, okay, we want to understand the relationship between pH and the ratio of how much of this weak acid is actually dissociated. Okay, so we start out with this Ka, and now we solve for H+. And so we basically just go through and say, we'll do a little bit of algebra, and so we say H+ equals Ka times HA over A minus. Now, we're going to take the negative log of both sides to be able to talk about pH. So now if we take the negative log of both sides, we can go pH equals, this is where you got to remember how logarithms work, pKa plus, or rather minus, the log of HA over A minus. So this is one way you can describe it. The more common way of doing it is actually to flip this and and change this sign. So the same thing is pH equals pKa plus the log of, now we flip this, of A minus over HA. And this is the more common form. So this is the Henderson Hasselbalch equation. All right, this equation here, that's a linear equation, so we can graph that. So let's see how that graph works. Now if we graph pH versus A over HA, we actually end up getting a curve that looks like this. because it's a logarithmic function. And the pKa ends up being this midpoint here. And this is the point at which A equals HA. Now, how do we actually change the ratio of this A to HA here? We can do that, like if we started with pure acid down here, we go up here with pure base, pure A minus over here. We get there by titrating with base. So if we put all HA in a solution, measure the pH, and then we start adding in base, what we'll find is that the pH will go up really quickly, okay, and then it'll kind of level off, and then it'll start going up again. Okay, because of this period here in which you can add base, basically, you can add base and you don't get any much of a change in pH, this is known as the buffering range. That we can add a little base, we can add a little acid, and you won't get a big change in pH. And it's generally plus or minus 1 pH unit from the pKa. So for something like acetic acid, the pKa equals around 4.8. All right, and so that what that means is this pH here is going to be 4.8, and it's basically from 3.8 up to 5.8 is when you're going to have this buffering capacity. This ability of this weak acid to take a solution and have the solution resist the change in the pH. Now, one of the things I want to emphasize, though, there are actually two things. Let me go back. I want to say operationally. Let me kind of introduce you one thing. So there's two reasons this is important for this class. One is that to understand that within the cell, where all our biological molecules are, it's a highly buffered system. There's a lot of weak acids and weak bases, and so there's a lot of resistance to change in pH. Okay, so that's one of the big things. Just sort of setting the aqueous up, understanding the aqueous environment in which all our biological molecules exist. The other one is more operational when you start getting into the laboratory. If you start taking biological molecules out of the cell and try to understand them by studying their studying how they their properties and stuff, all that. They like to be in a buffered solution. They're not used to having extreme changes in pH. So most of the solutions that you use when you're isolating proteins or nucleic acids, you put some sort of weak acid in their base to serve as a buffer to help control the pH of the solution. Now, you want to make sure to have enough buffering capacity. So there are two things that affect the buffering capacity of a solution. One is how close the pKa is to the pH. So, for example, if you want to acetic acid here works great if you want a solution at around a pH of 4.8. If you want a solution, if you want your solution to be any place from 5.8 to 3.8, 4.8 works just fine. The acetic acid works just fine because it has a pKa. But if you want to keep your solution around pH 7, acetic acid wouldn't work very well because at pH 7 you're going to be up here and you're not going to have very much buffering capacity. So two things affect the strength of a buffer, or the ability of a weak acid to serve as a buffer. One is how close the pH is to the pKa. You want it within 1 pH unit. And the second one is a little bit more straightforward. It's just how much. The more you have, the better. So the overall concentration of the buffer. So for those of you who are in 162, you'll be getting that, or for those of you going to eventually get into 162, you'll be talking about that in a bit. All right. Now what I want to do is kind of review. So we established the ability of these weak acids and weak bases to serve as buffers. And again, one of the reasons this is important because the cell is a highly buffered solution. So now what we want to do is we want to review the what are the different species that actually serve as buffering molecules, what are the different functional groups basically that serve as buffering molecules within biological systems. So this is so these are naturally occurring buffering . So one of the big ones is carboxylic acids. Just like acetic acid. So you have RCOOH goes to RCOO minus plus H plus. Now, the pKa of acetic acid, I told you, was around 4.8. Most of the carboxylic acids, most of the R groups end up influencing the pKa of these, particularly in amino acids. So in the biological molecules, the pKa is really range is maybe 2 to 5 for those molecules. So those will serve to buffer pHs around 2.5. The other one is amino groups. Actually, I'm going to write here just to make, this is the HA and this is the A. So this is the acid and that's the conjugate base. Because one of the things, you don't think of amino groups as acids, they're more weak bases, but you can put them in the same sort of format here. And now if you have RNH3+, this is your acid form, your protonated amine, and your base form is the RNH2 plus H+. In the pKa of these groups around 8 to 11. Now I want to add another one in here, carbonic acid, which is actually technically a carboxyl group, but it's kind of a special situation. In that if we take carbon dioxide plus water, you make carbonic acid. But carbonic acid dissociates into HCO3 minus plus H plus. The net reaction here is that we have CO2 plus H2O goes to HCO3 minus plus H plus. Now the pKa of this is around 6.35. This is important in buffering blood system, in our blood system. And it also contributes to metabolic acidosis. So if you're breathing really hard, exerting really hard, right, you're generating a lot of what? CO2. If you're generating a lot of CO2 in your blood, what's that's going to do to the pH of your blood? You're going to force the equilibrium of this to the right. You're going to generate more H plus, right? And so that's going to tend to acidify the blood. So that's one of the things that contributes to metabolic acidosis. Anyway, and so it turns out this relationship between carbon dioxide and carbonate is very important in terms of regulating the pH of blood in particular. All right. The other, let's see, we've got carboxylic acids, amino groups, carbonic acids. I want to talk about phosphates, because phosphates is a polyprotic acid. Start out with phosphoric acid. It can deprotonate and to form what's known as monobasic phosphate. So if we consider this as the HA, this is the A minus, we've given our H plus. The pKa of this is around 2.2. And this is a reversible reaction, so all these are reversible reactions. All right, now, but we still have a couple of hydrogens we can actually give up here. this is dibasic phosphate. PK of this is kind of an interesting story. You look up in a bunch of, if you go through and look up a half a dozen textbooks, you'll get a different pKa reading this. They'll cluster around 7.1, and the other ones will cluster around 6.86. Your textbook actually listed at 6.86, which I like. Because in 162, you're going to do an exercise pretty soon, if not next week or a couple of weeks anyway, in which you're going to be making a phosphate buffer. And you're going to have to use the Henderson-Hasselbalch equation to calculate the ratio of phosphate that you actually, monobasic and dibasic phosphate that you actually need for there. And for a long time, we used in that lab, we used a pKa of 7.1, because that was what came out of some textbooks like that. We were able to do the calculation. It never worked out. So then we started using the 6.86, and 6.86 works out great when people use that and then do all your calculations, make your buffers, everything comes out right. I've been trying to figure out why do all these books have a pKa of 7.1. I have never been able to figure it out. So operationally, and of course your textbook is, the one that I like is 6.86. But you'll see different places where they'll call it 7.1, and I don't know why.
Does it have to do with like time correlation, like previous books have?
No, I didn't see that. I thought it was a temperature effect or something like that. I mean, temperature do affect these things, but within the range that we see, it's relatively small effect. So I don't know. Somebody figure it out for me. And of course, this is a reversible. So the final one is when we have our tribasic phosphate here, and then this pKa is around 12.2. Now, you'll see when we get into metabolism and go through these molecules, there's a lot of phosphorylated molecules that we have. So like what's the basic energy currency of the cell? What molecule is that? ATP, right? You know, so adenosine triphosphate. So I have a triphosphate. So there's a lot of these ionizable groups. Most of the intermediates of glycolysis are phosphorylated. Yeah, so a lot of metabolic intermediates are phosphates, plus there's phosphates and diphosphates floating around. So this particular pK, 6.86, here is very important. All those phosphates are basically serving to buffer the aqueous environment within the cell. So it's a very important buffer within the cell. Now, the other thing I just wanted to do to relate this is let's look at the graph. So if we look at our pH versus the base added, our titration graph here, what we basically see is now we're going up here, we're going up here, and we're going up here, and then up like this. And so this is our first pKa, that's the one that's going to be around 2.2. This is our second pKa, that's the one around 6.86. And then this is our third pKa, that's the one around 12.2 or so. And then this represents the different species that are involved here. So right up here, we have tribasic phosphate. Okay, right here, we've got dibasic phosphate. And then right here, we have monobasic phosphate. Then down here we have phosphoric acid. Now, and these are known as polyprotic acids. Now your textbook, when it talks about molecules with multiple dissociable groups, so this is a molecule with multiple dissociable groups, it actually uses amino acids as an example, and it gets into and starts talking about PI, the isoelectric point, starts being that quantitative. I'm actually going to hold that discussion until we actually start introducing amino acids, and then we'll talk about the chemistry and amino acids, and we'll kind of go back and pick that up. So if you look on the homework, I don't think there are any homework questions that I have you actually dealing with polyprotic acids as amino acid examples. There is a lot of homework problems in terms of you actually being applying the Henderson-Hasselbalch equation to figure out what the ratio is to acids and bases and all that sort of stuff. So I'm not going to go through an example problem here. Have a crack at it. It should be somewhat familiar, hopefully, from some of your early classes. But don't hesitate to come to me if you get stuck, and we'll kind of go through and I'll help you work it out. All right. Oh, so what we've talked about here, all these naturally occurring buffers in cells, right? This is the stuff that's you know, and the application of this is how the environment of the cell, the pH is maintained within the cell. But then I told you sort of the other application of this whole discussion is operationally in the laboratory, how do you actually control the pH of the buffer? And I wanted to introduce you something that's actually not discussed in the text, but I think it's important, and that is goods buffers. So as I mentioned, if you're trying to study a protein or a nucleic acid and you've extracted it out of the cell, you want to keep it in a buffered solution, one in which the pH is controlled. And so a guy named Good, I think it's William Good if I remember right, an early biochemist, he decided that what he wanted to do is make some molecules that serve as good operational buffers. The problem with using something like phosphate as a buffer, phosphate is a great buffer, okay, 6.86, but so many biological reactions actually involve phosphates. And so if you have high concentrations of phosphates in your solution and you're trying to understand a reaction in which phosphates influence that reaction, it gets in the way, right? So what you want to do is find another molecule that can serve as a buffer that doesn't have phosphate. So he ended up synthesizing a whole bunch of these, and they're known as goods buffers. So these are synthetic buffers that have minimal interference in biological reactions. Other things that he was looking for are things like he wanted something that didn't absorb in the ultraviolet region, because a lot of assays, biological assays you end up monitoring the status of a molecule by monitoring the absorption in the ultraviolet region. And so he didn't want something that would interfere with that. So basically, he ended up, I'll show you some examples. Making some, and here's probably one of the most common ones. It's tris-hydroxymethylamino-methane, but everybody calls it tris. It's the tris buffer. Okay, and you'll see we use it in electrophoresis, we use it in sort of every place. And here's the acidic form. It's actually an amino group that is actually serving as the HA, it's the proton donor, and then here's the dissociated form. It has a pKa of around 8.08. So it's a little bit of a stretch to use that at pH 7, but a lot of things you end up doing at pH 7, between 7, 5, and 8, so it serves as a great buffer for that. Here's another one, MES, that has much lower pKa. Actually, it's a sulfonyl group here that actually is serving as the proton donor. it has a much lower pKa. And so if you're going to work around pH 6.5, 6 or so, that makes a great buffer. And you can basically go to the catalogs, like here's Sigma Aldrich's catalog, and they'll basically say, well, what pH do you want to work with? And you go, oh, I want to work with at pH 7. And so they'll basically have a whole bunch of these buffers listed here. So you want a pH 7, and then they basically have your plus and minus 1 pH unit listed here. And they say, well, these kind of work like this, but these would be a lot better. But these probably would be less good. You basically have a range there. So you can go and you can sort of pick out whatever buffer that you might want to use based upon its pKa. All right. Let me go introduce this last little section. So we've talked about water, the physical properties of water, some of the chemical properties, particularly ionization, and then how weak acids and weak base can serve to control the pH within a solution. Now what I want to do is talk a little bit about how macromolecules, so many biological molecules are macromolecules, think DNA, protein, tend to act in the aqueous environment. Some of the things that are important for that. So this is macromolecular interactions in aqueous environments. So some of this is pretty straightforward, like similarly charged macromolecules repel each other. Okay, so if you have a DNA molecule, we're going to talk about the structure of DNA in a lot of detail here, coming up pretty quick. And we've got a here's our DNA molecule. It's a double helix here. And what you will see is that physiological pH, the DNA molecule is quite highly negatively charged. It has a phosphate. It turns out that it has a phosphate on the backbone. Though I covered up my phosphate. And that phosphate is ionized. Actually, that's a key point in if you start to read the double helix. Pay attention to that because prior to Watson and Crick coming up with their structure of DNA, Linus Pauling published a structure of DNA that they determined was incorrect. And one of the things they determined, one of the reasons they figured that it was incorrect was because in Pauling's structure he had the phosphate on the molecule in a protonated state. And they knew that it was not protonated; it was actually deprotonated. Anyway, get you enthused about reading that book. All right. So if you have another DNA molecule that has a bunch of negative charges, I mean, it's pretty straightforward. They're going to repel. So they're going to repel each other, right? And similarly, proteins, depending upon, you can either have a net positive charge or a net negative charge, and so you can. So if they have a net negative charge, they can repel each other. If they have a net positive charge, they can repel each other. The final point here I'll make today is that, and again this seems like a little bit straightforward, is that opposite charges attract. So if we have a DNA molecule that has a bunch of negative charges, and we have a protein that happens to have a bunch of positive charges, that there'll be an attraction. And this is important, actually, as an example, are histones, which are important in DNA structure. We're going to get into that in a lot of detail. And so these positively charged proteins will interact with DNA and will bind to the DNA. Okay, we'll stop there. There's just a couple other points I want to make in this section, but I think you've got enough to get going. Remember, so the homework is due like midnight on Wednesday, so